Intermediate Algebra Section 3.5, Solving Applications Involving Systems of Three Equations. Systems of three or more equations arise in the natural and social sciences, businesses, and engineering. We're going to take a look at an example from the sports world. A basketball player scored 50 points in a game. The number of three-point field goals the player made was 14 less than 3 times the number of free throws made, each worth 1 point. Twice the number of 2-point field goals the player made was 15 more than the number of 3-point field goals made. Find the number of free throws, 2-point field goals, and 3-point field goals that the player made in the game. So we have 3 different things that we're looking for. We're looking for the number of free throws. I'll let that represent X. Y will be the number of 2-point field goals, and Z will represent the number of 3-point field goals. And let's go through the problem and see if we can come up with the 3 equations necessary to solve for our 3 unknowns. In the first sentence, it tells us a basketball player scores 50 points in a game. Free throws are worth 1 point, so 1 times X is X. 2 points per the number of 2-point field goals would be the points from the 2-point field goals, plus 3 times the number of 3-point field goals would be the scores from those are equal to 50. In the second sentence, it tells us the number of 3-point field goals the player made, that would be Z, was equal to 14 less than 3 times the number of free throws made. So we will take 3 times the number of free throws less 14. The next sentence tells us twice the number of 2-point field goals the player made was, and was is where we stop with an equal, so twice the number of 2-point field goals was 15 more than the number of 3-point field goals. And we let Z be our 3-point field goals, and it says it's 15 more. Well, let's get these equations lined up with our variables. We'll leave the first equation alone. It looks in good order with X first, followed by Y, and then Z. The second equation, let's bring the X to the other side. When we bring it to the left by subtracting 3X, we end up with a negative 3X, and the Z is equal to a negative 14. In the next equation, we need to bring, we'll call it number 3, we'll bring the Z to the left. It's a positive on the right. Subtracting a Z will make it negative on the left. So we have the 2Y. Bringing the Z over is the negative Z, as I said, is equal to 15. Now we're going to take a look at what we can do to eliminate these variables. And the first goal, to get this triangular elimination method, I want to get rid of this 3X. So I'm going to multiply everything in this first equation by 3. Multiplying it by 3 results in maintaining equality, and we end up with a 3x. 3 times 2y is 6y. 3 times 3z is 9z. And 3 times 50 is 150. Then we're going to add that to the second equation. The x's are gone. It leaves us with a 6y plus 10z is equal to 136. This is now our new second equation. We're going to leave our first equation alone. X plus 2y plus 3z is equal to 50. We have a new second equation. it is 6y plus 10z is equal to 136. And our third equation already has x gone, so we have a 2y minus z is equal to 15. Now we're going to target these two equations that only have two variables and eliminate one of the variables. And it really doesn't matter if it's the z or if it is the y that we get rid of. If we decide to stay with that pure triangular form, let's pick on the y then. And so I'm going to propose multiplying by a -3, so we get a -6 on our y here. When added to the second equation, we'll eliminate that. So the second equation is going to stay exactly as is. 6y plus 10z is equal to 136. The third equation, as I said, multiply it by a -3 will give us a -6y, or -6y, let me write that. Negative times a negative is a positive 3z. And the -3 times 15 is a -45. We're now ready to add the two equations together. The y's are gone as planned. Adding, we end up with a 13z, and 136 plus a -45 leaves us with 91. The only thing left now is to solve for z, since we have only one variable in this equation. So we'll divide both sides by 13 and leave us with z is equal to 7. Now we can funnel back through to find the rest of the values. Since we know z, which is our number of 3-point field goals, we can use that fact and plug it into either the third or the second equation. Let's put it right here in the third. Adding 7 to both sides will leave us with a 2y is equal to a 22. Divide both sides by 2. We'll end up with a y is equal to 11. That's the number of 2-point field goals. And then we can go further and plug it in z and y into an equation that has an x. Probably the first equation will do the trick for us. And that equation is x plus 2 times the y value, which we found to be 11, plus 3 times z, and we found z to be 7, is equal to 50. Simplifying the multiplication, we'll have a 22 plus a 21. Simplifying further by combining like terms results in a sum of 43 is equal to 50. Subtracting 43 from each side leaves us with x equal to 7. So to answer the question, which is important in a word problem, let's go back to the problem. It asks us to find the number of free throws. That was our x value we just solved for, which is 7. Find the number of 2-point field goals. That was y. We found that to be 11. And the last is the number of 3-point field goals. This particular game, there were 7 3-point field goals.